morning and welcome. I'm Casey Coates-Danson, Global Possibilities. Welcome to Global Possibilities' second annual Symposium for a Solar Future.
I'm a physicist, not an architect as far as training goes. And I went from Stanford to San Jose State University, where I founded the Department of Environmental Studies. And I chaired that for 21 years. And since I had my own department and could teach anything I wanted to teach, I started teaching solar design, solar architecture in 1973, and let that really take over my life. In 1991, the Union of Concerned Scientists, which was a 100,000 member organization for scientists who wished to spend some of their time in the public interest, some of their time and expertise. The union approached me about joining them and working for them on their staff, and I left the university, and I still am currently employed at the Union of Concerned Scientists. And it's a dream position. Basically, here's a salary and here's expenses, and go out there and make solar move faster than it would have if you didn't do it. I mean, it's really kind of quite a wonderful position. But my first love is buildings, really professionally, technically, personally, and design. And it is true, indeed, that I design buildings, although I need architects to sign off on drawings and things. And, buildings are incredibly important beyond just the fact that they're our whole built environment. They're important because they're so terribly underrated. All the time, people just ignore buildings. I was the opening speaker at the National Bioenergy Conference in Madison, Wisconsin, just a week ago or 2 weeks ago. And we did it at Frank Lloyd Wright's new community center. And so, as the last part of my talk, I introduced them to bioenergy and economics and why they're there and everything. And then I introduced them to their building. And I'd gone to Tony Putnam, and I got some historical drawings, and then I'd taken a lot of pictures myself. And I spent about 10 minutes, and I said, I want you guys to understand the building you're in. And I talked about it and showed drawings and showed pretty pictures and told them where to go at day and night and look at all the beauty of the building around you. And for the rest of the 4-day conference, many people came up and thanked me. They said, we've never thought about the buildings we're having conferences in. They're just rooms. And it was very, very refreshing to have something important be the place where they're housing us for the conference. And one of our real tasks has been to try to get this awareness of the importance of our built environment and the importance of our immediate environment to us, wherever we are and whatever we're doing, whether it's the classrooms we're teaching in or the offices we're in or the conference rooms where we're speaking and so on. Now, I'm really a policy person, and I speak to policy people, and I help write legislation and do things like that. And in all of this, I try to do two things. One is I try to introduce people to the reality and the urgency of the need to carry forward on the renewable energy transition. Casey just pointed out the ethical basis for it. Of course, we have an obligation to those who follow us. But it is a terribly urgent obligation. We can't wait for those who follow us to accomplish it. We really have to trigger it. And so when I looked at and had this assignment to be at this group and looked at the list of who's going to be here and realized this is not just an audience. It's not just an audience of peers. It's an audience of superiors in some cases. And I won't tell you whom I consider peers and whom I consider superiors. And I thought, what am I going to do for the group? And then I decided I'll do two things. I want to lay out a little climatology for you, if you're not already convinced. I want to convince you so convincingly that in your programs and in your classrooms, you will also convince your students that climate change is real, incredibly dangerous, and the greatest global environmental threat that we have ever faced. It's also the greatest global economic threat that we have ever faced. And if you're not fully convinced now, I want to do things for a few minutes to convince you. And then I want to show you the way I take that argument. I do that argument always. I'm going to go in a little more detail with you. I mean, if you're doing a half-hour talk for a business group, it's obviously somewhat more condensed. But then I'm going to show you how I segue into buildings. And no matter who I talk to, no matter what the audience is, I segue into buildings. Because buildings are the most direct place to start mitigating climate change. We can have our greatest impact for the least cost in the shortest time in mitigating climate change if we start with our built environment, both the existing built environment and those buildings that we're still going to do. And that's partly my own agenda of just trying to get across to everybody to start paying attention to these structures that you're in. And not just what they do for you when you're in them, but their extraordinarily important role to society, to the economy, and to the environment. So with that as background, I'm going to switch to slides, and these bright lights, I'm told, are going to come off. It's a fine topic. Solar is a fine topic. Good morning, my favorite antidepressant. All right, you can take pills in bottles, but you all know the best thing to do is to go outside and just take a look at that marvelous thing up in the sky, and it's uplifting and nourishing and all sorts of wonderful things. Now, when I was preparing to come talk here, Carolyn Ward was talking to me on the telephone, and I don't know how we got into mentioning about the electric car that I drive around in these days. That's a GM EV1. But I thought I would put it in as a bit of history, because this is the second in the series of 4 conferences put on by Casey Coates Danson. And the first one in Santa Barbara, Ed Bagley came driving up in his EV1. And I went for a ride in the EV1, and I thought, if I ever move into the city, I've always lived in the country, if I ever move into the city, that's the thing to do. And as it turns out, I moved into Berkeley just this last year, and I thought, okay, that's what I would do. But the advertisement for the EV1 is you can't hear it coming. Okay, you can't hear it coming. And Carolyn said, you know, that's a good metaphor for the environmental problems and for the renewable energy transition. You can't hear them coming. Indeed, we realize as we look ahead and compare the needs that society is going to have for energy with the availability of energy, at least from conventional resources, this portends total economic collapse. And we can't hear it coming. Nobody's paying much attention to it. And yet it's incredibly dangerous. So there's a metaphor, and there's an excuse to show the electric car. And later on in this, you'll see why I've done that. I'm going to come back to the energetics of the electric car. All right? Well, I think it's useful to step back a little bit and realize that it isn't a question of what are we going to do when we transition out of the fossil fuel age, but the first thing to do is to get the perspective that the fossil fuel age is the transition. Many people don't realize this. The whole industrial development of the world all the way to the middle 1800s was done on available and renewable energy resources. And now we've entered the fossil fuel age. We already see that we're going to be going out the other side. The expectation is that global production of oil will peak in the year 2003, and then it will start to decline while demand goes up. When supply declines while demand goes up, there's the start of your economic chaos. Pretty close right now. And anyway, we're going to come out the other side without oil. We are gifted, however, to have an abundance of an incredibly convenient resource like oil and gas to transition us, to power the transition between what you might call a pre-industrial age and a post-industrial age. And if we use this the way it should be used, we can accomplish this transition. If we just burn the stuff up in our vehicles and our buildings and our industry, and then ask, okay, we're here, now what are we going to do? We've had it. And it is this danger that you can't really hear coming. Everything that we do with energy pours stuff into the environment, everything. When we create energy, it pours stuff into the environment. When we use energy, it pours stuff into the environment. In some cases, it sticks around locally. We've done a pretty good job of getting rid of the worst of that. But what we can't see continues to go into the environment. And we now do things on a human scale that's so great that our emissions into the global atmosphere are altering the composition of the atmosphere. And this is the tracing for the last 130 years or so of just one of them, of carbon dioxide into the atmosphere. Gone from 280 parts per million up to around 360 parts per million. Small amount. I mean, we're mostly nitrogen and oxygen and argon, after all, in the atmosphere. This is just a small amount. And it's incredibly important for living things and plants. If we increase the quantity there, like the coal people like to tell us, it makes plants grow better, which is exactly true. So why worry? Well, I'm not talking about worrying yet. Let's just look at what we're doing. We're increasing carbon dioxide. We're increasing the abundance of nitrogen oxides into the atmosphere. We're increasing the abundance of methane into the atmosphere, mostly thanks to cattle, but we're grazing many, many more cattle for all those hamburgers that we like to eat these days. All right? And we're increasing the abundance of stuff that never existed in the atmosphere before. chemicals that are alien to just the way that the Earth is used to working. In CFCs, for example. And the 4 primary greenhouse gases, what we call the greenhouse gases, are the ones you've just seen, are carbon dioxide and nitrogen oxides, and methane and CFCs. Now again, these are all in parts per million introduced in an atmosphere dominated by other stuff. Why do we care? The Earth is at a very delicate thermal balance, right? I'm sure you all realize that the amount of energy coming in equals the amount of energy that goes out. Now, this is a trivial thing to say to this audience, but now suddenly you have to imagine that you are a business audience, you are an audience of legislators, you're people I'm talking to, I'm trying to convince. And this for them is something new. By golly, the same amount of energy that comes in goes out. And I will say, well, if it didn't, if more energy went out than came in, you'd get colder and colder, folks. And if more energy came in than went out, you'd get hotter and hotter, right? Therefore, we're at a very, very delicate balance. And all of the mechanisms, energy distribution mechanisms of the Earth and energy-using mechanisms, have accommodated to that balance. And anything you do to disrupt the energy flow, physics requires that the balance changes. And this is how I kind of do away with what you might call the greenhouse arguments. People like to say we don't have enough scientific research, there are different opinions on both sides. I like to present things in a way that people will realize that it's incontrovertible. Right? We are changing the energy flow. We're introducing more aerosols and dust and soot, which affects the flow coming in. And we are introducing what we call the greenhouse gases, which have a molecular interaction that reduces the ability of the infrared to flow back out. And it turns out this is a bigger effect than that one. Therefore, we are unbalancing these two sides, even though we're affecting both sides. Since we are changing the flow of energy through the atmosphere, it is a straight physics statement that the Earth must respond. That is just plain physics. Nobody can argue that point, and nobody does. The coal industry that likes to send people along and dog me when I'm appearing before legislators and so on, right? The coal industry will admit the same thing. Yes, we're changing the flow of energy through the atmosphere, and therefore that the Earth must respond. That's just straight physics. So it places the whole climate change issue on one of a global roulette. How will the Earth respond? Will we like it? Will it be fun? Will it be good for economies or bad? And everything that we look at suggests it will be devastatingly difficult for human societies and human economies to accommodate to. Well, how is it going to respond? We try to guess how the Earth will respond to reducing the flow of energy back out. One way is to look at history and look at the relationship of the temperature of the Earth back to 150,000 years ago to the carbon dioxide content. They've been able to get these from bubbles in ice, for example, and glaciers and things, all right? And you find for at least 150,000 years there has been a correlation between carbon dioxide content in the atmosphere and the Earth's temperature. Which drives which? No one really knows, and it doesn't matter. You get more carbon dioxide, and therefore the Earth gets warmer, or the Earth gets warmer and things grow better, and therefore more carbon dioxide. It doesn't matter. All we know is that there is a synergistic response in the Earth's climate and the amount of carbon dioxide in the atmosphere. And that's how it was for 150,000 years, but whoops, here we are right now. I'm sorry, there we are in 1800. And there we are right now. So we've already moved ourselves to a point that's outside anything we've seen for the last 150,000 years. We have no historical record to tell us what's going to happen, but there's evidence that that statistical relationship is continuing. Right? So the first thing you would expect is if you retard the flow of energy out is that the Earth will get warmer. And so we find ourselves looking at temperature statistics, and indeed there's been a monotonic increase of some interest over the last 100 years or so. And especially, it's picked up especially recently. The hottest year on record was 1997. 1998 has been hotter than 1997. The hottest month on record for the last 130 years was July of 1997. July of 1998 was almost a half of a degree warmer. Every single month of 1998 has been hotter than every single month of 1997. So we are seeing evidence You can't call this scientific proof because there's all sorts of perturbations to the Earth's climate, but we're seeing evidence that's fully consistent with what you might expect. The evidence of the temperature rising abruptly and faster than any time in the world's history, in response to the carbon dioxide rising faster than any time in the world's history. So those are scientifically consistent. Okay? And I thought I'd put this in perspective because we're asking ourselves, where do we go from here? And we have the Kyoto Protocol where we're trying to back things down to the 1990 level, which is right here. And if we don't back down to the 1990 level, business as usual is going to take us up to there rather rapidly. And that will be a greater concentration of carbon dioxide in the atmosphere than we've had in the last 50 million years. And it will have been accomplished in 100 years. A totally impossible geologic time frame for anything ecologic to respond. People are doing models, and we're getting pretty good at the models. And the models are trying to guess what would be a reasonable expectation for temperature increase if we continue as business as usual. And the most likely rise you all hear about is around 3 degrees, 3.5 degrees centigrade, 5 degrees Fahrenheit. You call that the most likely. And most likely because it seems to appear more often in the models or as an average of the models. What does that do to you? Well, that makes you feel kind of uncomfortable. For example, Washington, D.C., that only has one day over 100 degrees each year, you would have a dozen days. But actually, let me put that in perspective. That's just with a doubling of carbon dioxide. If we continue with business as usual, we could quadruple the carbon dioxide in the atmosphere. The average temperature in Washington, D.C. in the summer, in the days, is 85 degrees. If we quadruple the carbon dioxide, the average temperature will be about 110 degrees in Washington, D.C. Okay? So this is a little bit more than just a comfort issue. We're certainly going to notice it. Well, I've been told you just turn on your air conditioners, just run them a little bit more. Oh, fine, okay. Well, other things happen. When the climate gets warmer and warmer, even though we're cleaning up the environment, we get increased photochemical reactions. It's just chemical reactions work better when they're warm. And so we have much more serious air pollution problems. And so we begin to do calculations as to what's going to happen if we put more carbon dioxide in the atmosphere and the climate response. How about human deaths? What's that going to do? We start calculating them for areas. This is the Los Angeles basin, San Francisco basin, and we find that statistically we expect we're going to have many more people die. The greatest killer of people in the United States right now is air pollution. All right? We have 100,000 people a year killed from air pollution. We have 50,000 people a year killed from automobile accidents and so on. So we begin to convert simple things like a temperature rise where people tell me, so what, 3 degrees, big deal. You begin to convert it to things that really relate to the human experience. As the oceans get warmer, they expand. Water expands when it gets warm. And of course, we also are getting melting from the ice caps. And so there's a good expectation that the ocean surfaces will rise by about 1 meter, somewhere in there. They've already risen between 4 inches and 12 inches in the last 100 years. And people will say, so what? Whoa, I'm trying to go backwards. Sorry. We'll say, so what, with a 1 meter rise in ocean? Well, if you live in Florida, there's quite a so what. Everything you see in red in Florida tends to vanish. All right? If you live in Bangladesh, it's more serious. You lose about half of your country. If you live in some of the islands, in the South Sea Islands, you lose your entire country. That's what a 1 meter rise of sea level can do. Well, what else? Suppose the temperature is only 3 degrees warmer. I mean, again, big deal. 3 degrees, as I said, you turn up your air conditioner. Tell that to the snow. Present snow level is here. 3 degrees centigrade warmer moves it up 1,500 feet vertically. All right, if you're in the Sierra Nevada, that reduces the snowpack accumulation by 70% because what used to be snowpack accumulation becomes rain that runs off and increases the winter floods. So you reduce the snowpack accumulation in California by 70%. With a 3 degree rise, and therefore the present flow in the main California rivers, which provides the water for California agriculture, becomes this flow. And a 3 degree rise will probably reduce the ability to store water to the point where a $19 billion a year agricultural industry goes down the tubes. 3 degree rise could destroy a $19 billion industry in California. You're beginning to see what I'm doing. Wherever I am in the country, I will relate the potential impacts of climate change. You notice I use climate change rather than global warming, but the potential impacts to whatever region you're in. Now, you've been given handouts that also help you identify your climate zones, which is really quite neat in here, your ecological zones. Okay? Here's another thing. I mean, ecology is balanced according to the climate. So what happens with a 3-degree temperature rise? 3-degree temperature rise, let's go up to Oregon now. Let's go up to the Pacific Northwest, John and company. All right? You've got your commercial forests down here, and they're being logged, but you give them 50 to 100 years to climb from there to there because they have to reach a new ecological zone. And if they can't do that, then they have to go north by 300 to 500 miles, entire forests. And if they can't do that, then they just die out, and they have to replace themselves with an ecological species that can make it in the new climate. And that's asking a whole lot. So that when I'm up in the Pacific Northwest, I will tell environmental leaders we ought to be telling the loggers to work with us because they're going to lose their industry because of the impact of energy as well. Right? Okay? Current and projected ranges of sugar maple, the beautiful fall colors that you get, also important for tourists and for the maple sugar industry, maple syrup industry. Here's where it is right now, and if you double the carbon dioxide content, the maple forests are going to try to move from there up to there. And if you quadruple the carbon dioxide content, I'm sorry, this is doubled, but this is just based on temperature. And as I'm going to show you in a minute, if you allow for the change in precipitation along with temperature, this area here becomes that. And all the sugar maples vanish from here, and they all try to move up there, and they got 50 to 100 years to do that. And that's asking a whole lot. That's stressing ecological systems at an extraordinary rate. This is going to be a massive die-out down there. We're lucky if that even materializes up there. How good are we at sort of making these models and these estimations? A straight predicted temperature rise off of putting carbon dioxide into the atmosphere would look like that. But we're getting very clever with our models now to put in aerosols and other things. And we now, with our models, are able to say this appears to be historically what we would have predicted for the temperature rise, and there is the temperature rise. And therefore, theory does seem to agree pretty well with history, and we can, with some confidence, project those on them. So these models and these projections, ecological and climate projections, are not just fantasy. So we'll take those projected models, we'll say we'll double the carbon dioxide content, and ask about the surface warming. We're differentially warming the northern half of the world, and especially when you get way up there. All right? Here's the United States up here. And this shows a warming in the United States of between 5 and 10 degrees on the average across the United States with a doubling of carbon dioxide content. Now, what happens when you warm is you evaporate more efficiently. If you evaporate more efficiently, you dry out soils. And so you're going to get a reduction of 10 to 30% in soil moisture in this area of the United States, in this, all right? People will look at temperature and just say, well, if temperature changes, so what? But everything changes. So soil moisture changes. So now we're trying to grow food, and we have a reduction in soil moisture, which means we've either got to irrigate more or move food growing up to Canada. And it gets worse if we go to 4 times the carbon dioxide increase, which we will on the present path that we're on if we don't get serious about leveling it worldwide. And 4 times the carbon dioxide increase increases the average temperature in the US by 15 to 20 degrees, soil moisture content reduced by 30 to 60%, and you can forget about growing food in the US, folks. We'll just have to get our food from somewhere else. Well, then we begin to ask ourselves, where is the somewhere else that we're going to get our food from? So we can look at what's going on and expect it to go on in the world. And it's rather interesting. The total ability to grow food in the world may not change substantially. It migrates northward, all right? So that everybody becomes importers of food. But the ones that are going to be most affected, where you expect to have the greatest impact on agricultural productivity, South America, Africa, Asia, in other words, almost all of the developing nations of the world are anticipated to have the worst time in trying to keep up with agriculture and growing food for their people just at the time that they're trying to develop. Well, it's always been a bit of a mystery, at least to some people. Why is it that the injection of carbon dioxide is so extreme, but the temperature response isn't as extreme? Now, we're seeing this year and last year that it may be getting extreme. And the reason for that is basically when you're just looking for temperature signals, you're looking at the wrong thing. The Earth uses climate as its way to distribute its energy. That's what climate is, right? You warm the surface of the Earth, you warm the air moves around, it starts moving in global patterns, it drags the ocean until you have ocean currents. So climate is the Earth's mechanism for distributing energy. The Earth doesn't want to get warmer. No physical object really wants to warm up. When you change the set point, what it does is it redistributes its energy as uniformly as possible. We have a greater concentration of energy, of course, in the equatorial areas, and as we increase that concentration, by reducing the ability to lose it, the Earth is going to more violently try to redistribute its own energy. And so climate is the area where we really expect and anticipate and think we already see major changes. For example, the incidence of rainstorms of 2 inches or more, which is a flooding rainstorm in the United States, has increased by 20% just this century. All right? The incidence of hurricanes, it's difficult to say, but hurricanes are appearing with regularity, and they're especially violent ways of redistributing energy, and especially worrisome to the insurance industry. And the insurance industry of the world is now leading the campaign to reduce carbon dioxide injection into the atmosphere because the insurance industry of the world makes its living from risk. And they can't tie their future projections to the past anymore. They've lost that coupling. They don't know how much to charge for insurance. They don't know how much risk that they can afford to take as a business. So you'll notice as soon as a hurricane goes through the east coast of the United States, all the insurance companies stop insuring you for hurricanes. As soon as we have earthquakes in California, the insurance companies stop insuring us for earthquakes. They simply bail out when these things happen. And the insurance industries, they make their business from risk. Well, so do the rest of us. And the principal economic message I try to give to business groups and legislators is we are all making our business from risk and from managing risk and assessing future risk and determining today's policy. Well, I'm going to finish off this climatology thing with what to me has always been the most convincing example that you don't have to sit around and wait for proof that climate change is happening. It's been right under our very nose for 40 years. If you take the rainfall, remember that as it gets warmer, we evaporate more, we put more energy into the atmosphere, more water, moisture in the atmosphere. It tends to migrate northward, all right? We group the rainfall into latitude bands. Here's the equatorial band. Here's the southern latitude band. Yes, you're down there, Jeff. Arizona's in there. Northern latitude band, John Reynolds and company up there, all right? And we find statistics, rainfall statistics for 130 years, just sort of, or 120 years, just bouncing around there. When we get up to the southern latitude bands, it bounces around until here, and all of a sudden we have a statistically significant decrease in rainfall. But don't worry, it didn't go anywhere. There's the mirror image of it. It is there. It walked north. We have a statistically significant increase of rainfall as it walked north. Now let's go back to this one and see that the major post-World War II industrial development, let me try to focus a bit. The major injection started right around in here, say around 1950 or so, or the major change to the composition of the Earth's atmosphere from our post-World War II industrialization. So let's just lay this, I'm sorry, I don't mean to keep pushing that. Lay this on to where the statistically significant change started to happen, and we come down there, there's 1940, 1950, 1960. So for 40 years, we have had a statistically significant migration of rainfall that is exactly consistent with all of the models. And I don't know how much more research we need to have before people can be convinced that this is real stuff. It's really happening, and the Earth is really responding. So how do we respond? And who should be the ones who respond? Well, Not surprisingly, the world emissions in '95 is dominated by the developed nations, and the United States is the granddaddy of them all. So if we really want to try to help the world, or lead the world, if you will, on reducing emissions into the atmosphere, reducing the threat, the biggest opportunity is here in our own country. We've got to get our own house in order. Because if we don't, then we go up to 2035, which is less than 40 years from now. We're still injecting into the atmosphere, but the developing nations have developed like mad. China, with all of their coal-fired power plants that they're building right now, will have displaced the United States as the greatest contributor to emissions into the global atmosphere. And this is the scene that it will be, unless the nations that are here can show that you can have a strong economy and social equity and sufficient food for people under very different ways of doing things. If we begin to demonstrate that ourselves, we reduce the danger to ourselves from the developing nations who would also follow business as usual. So it is also a great risk mitigation to the developed nations to get our own house in order, and in order to help show the developing nations that they don't have to make the mistakes that we made. We're all in this place together. So we look at the human contributions to greenhouse gas emissions. Carbon dioxide is the biggest one. Nitrogen oxide, not so big. CFCs are big because of the power of each molecule of CFC. It's got 6,000 times the global warming effect as each molecule of carbon dioxide. Methane is important because each molecule of methane has 20 times the global warming potential of each molecule of carbon dioxide. So it's not just the amount you inject, but it is the impact of what you inject. But the primary thing we're putting into the atmosphere is carbon dioxide. We can make the biggest difference there, perhaps the quickest, by reducing carbon dioxide, and we ask how to do it, and we say, here it is. Causes of climate change or energy. So now we've identified an enormous risk to the world, and we've come back to the developed nations and say we're all in this together, and the risk from our own actions and the actions of the developing nations is equivalent. We got to get our own house in order. Where do we start? We start with energy. I started this talk by saying buildings are incredibly underrated. People pay no attention to buildings. I could just as well have said energy is incredibly underrated. Policymakers pay no attention to energy. They don't pay any attention to energy economics. They don't pay attention to the impacts of energy. Right? These things fold together. Causes of climate change, let's start getting our energy house in order. So we look at U.S. energy supply, and it's no particular surprise to anybody. Petroleum, natural gas, coal, dominated, of course, by the very resources that are causing the emissions into the atmosphere. It's nice that we get more energy from renewables than we do from nuclear, and that balance will continue to tip in the favor of renewables, but we have got to dramatically accelerate that and somehow dramatically reduce this. Well, the moment you start talking about reducing it, people worry about shortages and crises. Many of us remember, most of us in this room remember the gas lines in 1973-74. We behaved very badly in times of shortages. It's every person for himself or for herself. Do you remember we had to pass a law in winter '74 that made it illegal for you to go to the gas station if you had more than half a tank full of gas? Because people would stay in line for 3 hours to get with a 10-gallon tank to buy 1 gallon because they needed the security of feeling that that tank was full. And the storage of oil in the United States shifted into the gas tanks of cars. So we have to know that we have to make changes that avoid crises. Avoid crises. People are scared of crises, and the worst in our behavior comes out in crises. Well, what we did is we began to take efficiency seriously, and I'll show you another graph in a moment of the history of the efficiency that we introduced after that winter, '73-'74. We got scared. And we've done pretty well with efficiency, but here's where we are. It still takes twice as much energy per capita in the United States. Well, of course, that's because we're twice as wealthy as Japan, Germany. Oh, wait a minute. Maybe there's not a one-to-one correlation of energy use and wealth. And it takes twice as much energy to produce a dollar into the economy in the United States. I'm just trying to focus a little better. Okay. As it does to what you might call our second-rate economic competitors, Japan, Germany, other places like that. And this hurts. Why do we have to spend twice as much to create a dollar, twice as much energy to create a dollar as they do? The energy that they don't use, they can take those dollars and pour them back into their economy. But you know what they do? They tax themselves extremely highly. So the cost per energy per product manufacturer is about the same in the different countries. But then they use the revenues from the taxation in order to pursue their social causes and also to provide themselves with a buffer of a sudden increase in price of oil. We have an increase in price of oil, and our economy has an enormously difficult problem. Italy and Japan and Germany has a huge increase in price of oil, and they can immediately lower taxes, and they can buffer their society and their industry by their policies, by the way that they charge for their energy. Well, we haven't paid any attention to our energy economics, and what I try to do at this point in my presentations to businesses and legislators is to say that if I haven't convinced you about environmentally responsible action or the need to take environmentally responsible action, let me just talk dollars in economics. Let me just help us clean up our economic act a little bit. As we increased our use of fossil fuels in the United States, we were fine until here. We had enough energy to power our own society and our economy until about 1970, and then we didn't have enough. And so we simply started importing it. And from 1970 to 1980, we became a debtor nation. And by the time we got into 1980, we were spending around $80 billion to import energy resources. And our policymakers said, that's okay, because it's the energy that powers society. And we all say, wait a minute, that $80 billion, if it was spent for United States energy resources, multiplies itself and folds back through our own economy. This is an enormous loss of economic activity. On the average, you lose $1 of economic activity for every dollar that you send out, or every dollar that you have to import something. So that's probably a $150 hit, $150 billion hit to the US economy. It's something very important. It isn't just that the energy drives the economy. And I like this cartoon because it puts us in perspective. Cost for gasoline, $1,001.29 for regular, $1,001.39 for unleaded. The gas is only $1.39. The aircraft carrier is $470. The tank is $125. The stealth fighter $330. Gas mask $45, and the gun adds $30 a gallon. We figure we spend 1/4 of the National Defense Fund protecting our access to the Middle East. 1/4 of $250 billion a year, something like $60 billion a year, to protect our access to oil. Right? What does that do to the cost of oil? Well, I'll tell you, it's not $17 a barrel anymore, folks. During the Iraqi war, for example, if you took the cost of the Iraqi war and laid it out the cost of oil, all of a sudden we're willing to spend $50, $80, $90 a barrel of oil, because we don't take into account what else we pay to protect our access to that oil. It's a huge economic impact by not using our domestic resources. So we go find more domestic resources. We go up to Alaska. You annex something that's got oil, and then you've got it. It's domestic. Hawaii does not have oil, even though we've got Hawaii in there now. And I was born in Hawaii, by the way. I'm very favorable toward it. So we go and find more oil, and we practice what David Brower likes to call the politics of exhaustion. We'll use it until it's finished, but there's another way to go about things. And this slide, this pair of slides, I think I show to every audience I talk to. I say, let's go to every house in the United States that uses oil for heating itself. And let's go to every one that's got single glazing and is not weatherized. And let's go back and let's replace the windows with double glazed windows, and let's weatherize that place. How much oil could we save in the United States? And that's the answer. It's about equivalent to the Alaskan pipeline, which means we have another Alaskan pipeline sitting there in our houses. But there is a different way to look at this. The way to look at this is to say you can take all of that oil, a $10 billion pipeline, if you will, The equivalent of all of that oil, and what's its economic value? Nothing. Because its purpose is to leak out through windows. That's the purpose of an oil equivalent to the Alaskan pipeline, is to leak out through windows. It does nothing for economy. If we weatherize our buildings, if we reduce the use of oil in buildings, then the oil that was being leaked out can go back into society. It can drive vehicles. It can power industry and commerce. And all of a sudden, you've got economic value from it again. That's a huge external economic value to weatherizing homes. We talk about how nice it is when you weatherize a home. It makes it more comfortable. It reduces the energy bills for the people living in it. We never talk about what it does for the rest of society. It puts money back into society. It creates jobs. It creates industry. Let's step back and look at how we use our energy and start asking maybe where we should start putting our effort to reduce energy use, to reduce the emissions into the atmosphere by the US, and perhaps to help lead the world. This is a little old in numbers. The number of quads now is all the way up over 90, maybe 91, 92, 93, somewhere in there. All right? But the distribution of energy use. We pay a lot of attention to reducing energy in transportation. That's especially where the oil goes. About a quarter of our energy use goes there. And we get maybe 35% of our energy use or so going into industry, and the same amount going into buildings. Now I want to snap my finger and say, come on out. Let's have the quickest response we can have to becoming a more efficient society at the lowest cost and reducing our emissions into the atmosphere. This is tough to change. This is pretty easy to change. This is pretty easy to change. And this is lower cost even than this, and this has potentially a bigger impact than this. So I will tell decision makers, if you want to start passing laws and regulations and doing things right now to have the greatest impact, come up here immediately. Start looking at your buildings and looking at your building energy use, and at least clean up your Building Act. A calculation was done by what was then the Solar Energy Research Institute in 1980. It's now called NREL, as you all know. And that was that since California had adopted energy efficiency standards for buildings in 1977, suppose the US adopted the California standards in 1980, then looking at all the new buildings that would be built under those standards over the next decade, how much energy could be saved? The amount of energy that could have been saved in buildings exceeded the total output of all of the nuclear power plants in the United States. The amount of energy that could have been saved in buildings was equivalent to about 80% of all of the energy used for coal-fired power plants, and on and on. It could have displaced 2/3 of the oil imports, for example. In other words, the potential energy supply equivalency of conservation in buildings is enormous. And this is a lost opportunity because we didn't do it. 1980 came and went, and 1990 came and went, and the United States didn't adopt the standards. We've gotten pretty serious about building standards since then, and we're doing a lot better. But every year we don't adopt rigorous standards for building energy efficiency, we're throwing away a huge potential displacement of the very supplies that are giving us trouble. Now, this is a historical view of what we did with our energy efficiency. This was the basis of Ronald Reagan's view and everybody else's view that if you want a stronger economy, you've got to have more energy used. Because indeed, energy use and economic growth tracked exactly until we hit the economic dislocation, the problem, the oil crunch, in 1973. And then we got serious about energy efficiency. And we leveled our energy use for a magic 13-year period, almost 15-year period. But the economy continued to grow by 34%. And for those skeptics, this proves that efficiency can power economic growth every bit as much as energy supply can power economic growth. What is efficiency? Efficiency is taking the dollars you didn't have to spend for the energy, folding them back into other sectors of the economy, and the economy continues to grow. How much should we save? Well, you can look at 31 quads of energy. If that doesn't mean much, that's $150 billion a year. $150 billion a year less for energy we're using because we began to take energy efficiency seriously. And how seriously did we take it? 2% per year. All we did was clean up our act by a very modest 2% to 2.4% per year, and we managed to level and break this relationship between energy use and economic growth. And we managed to reduce our electricity use by about $100 billion per year. Buildings use 2/3 of all of the electricity in the United States. So this is already proof of some of the benefits of our energy efficiency in buildings folding right back into society. So it says, to do this economically, what you want to do is to look for the least expensive ways to start. And obviously you start with energy efficiency. If it's less costly to give the same services with energy efficiency than it is with supply, you're an idiot to spend the money for supply. You might as well save your money. And so we have scenarios for saving our way through energy efficiency. Well, it's rather interesting to see how much potential we have. Here's the $150 billion a year we're saving right now. If we chose to be as efficient as some of our other economic competitors, like Japan, there's another $220 billion per year waiting to be tapped using today's technologies and waiting to be tapped economically. Wouldn't it be wonderful to fold that $220 billion a year back into the US economy? So we begin to have an alternative way of presenting efficiency, and I'm going to segue into renewable resources, so don't worry, Casey. Solar energy is really going to surface out of all of this. Okay? Energy efficiency means jobs and business. Now, who put out that brochure? The state of Nebraska. Can't remember. Do we have someone here from Nebraska? No? All right. Nebraska was going bankrupt in the 80s. They're an agricultural economy, and it just wasn't keeping them afloat. And they realized that they had to keep their dollars in Nebraska. And they realized how many energy dollars were going out of Nebraska. And so they developed a program for going into weatherizing homes, not because it makes you more comfortable and saves you money, but they sent to every homeowner in the state of Nebraska, they sent this brochure. Please let us come weatherize your home because your savings creates jobs and business for us in your state. And that message begins to be the message that gets the attention of the business people and the industrial people and the politicians, far more than the environmental message, I'm afraid to say. Now, we have our own messages on spending money. Part of the problem with energy efficiency and with renewables, of course, is you've got a higher first cost. So you can go out and pay more for a compact fluorescent lamp, but it can outlive a whole bunch of incandescent lamps. And in the process, it's a far better investment than anything you have got. It's far better than any CDs, any stocks, any bonds. Is investing in energy efficient appliances is the best place you can put your money as a starting point. Now, isn't that nice? Because you can have a better investment in your own home, you can save more money, all right, than you could otherwise, and in creating the same amount of light for every light bulb that you change over, there's 400 pounds of coal, and therefore the emissions from 400 pounds of coal, which is over 1,200 pounds of carbon dioxide, from changing one light at home. And what moves you to change that light? Well, environmental altruism could move you to changing that light, or just wanting to save energy. But you've got to be willing to spend a little bit more money at the beginning to accomplish that, and yet you end up saving your way into mitigation of climate change problems. There are a lot of very serious economic studies out right now. The Energy Information Agency just came out with one, and the Union of Concerned Scientists really had to attack them for that. It's garbage in, garbage out. And most of these are essentially showing how expensive it will be for the U.S. economy to meet the 6% or 7% reduction we've promised in emissions of carbon dioxide. And when we do our analysis where we fold in energy efficiency and the economic benefits of efficiency, and we fold in an accelerated development of renewable energy industries that will follow, we find ourselves saving our way into meeting the Kyoto Protocol. We believe the United States could save something like $1 trillion while meeting the Kyoto Protocol. Save, not spend. So we've got this great argument now of economic models, and that'll be fun to watch. Okay? Efficiency makes renewable energy affordable. There is a relationship between them. If you're going to live away from a power line and you want to have electricity because you want to have electric lights, and so you say, all right, I need 4 panels, 70-watt panels, let's say, for my place. That's maybe $250 a panel. I need about $1,000. No, 70-watt panel, a lot more than that. They're about $600. So about $2,400 worth of electricity, of photovoltaics to bring electricity to my cabin. And you go to the utility and they'll say, for $2,000, we'll bring a line. And then you got your electricity. And so you go to the local utility instead. Then suddenly you realize that what you want is light, not light bulbs. So you're willing to get light from something that's a little more efficient and a more efficient sunfrost. Let's say there's a cabin, sunfrost refrigerator, and a few other things. And all of a sudden you only need one $600 PV panel. You go back to the utility and you say, I'd like electricity, and they will tell you, we told you it'll cost $2,000 to bring the line in, and now you say no thanks. So you crossed yourself over from being uneconomic to use renewables to being economic to use renewables, using efficiency as the mechanism to cross you over. Now that's a simple way of saying in our economic models that's what happens on a large scale. As society undertakes efficiency seriously, we find a rapid acceleration of the application of renewables that is dragged along by diminishing this cost differences and moving the crossover point earlier. Efficiency and renewable energy goes hand in hand. And especially when we get back into buildings, because we don't know what we're talking about. Is this solar energy supply or is this efficiency? I mean, the sun is supplying heat, so your furnace doesn't have to run, fine. Or your place is naturally warm, so your furnace doesn't have to run. Okay? So there's a supply view or efficiency view. Mathematically, they're identical. Mathematically, they're identical. And so when we go into our buildings and start using solar energy and thermal energy and daylighting and so on, these are efficiency measures. People tell me they're efficiency measures, and I say, fine, I don't care what you call them. But it's also helping us build a solar industry that's extremely important. This is a house I lived in for a number of years when I was young. It's Frank Lloyd Wright's solar hemicycle, designed in 1943-44. And I wrote, monitored it and then wrote some papers fairly recently about it. But this was a house using all of the techniques of passive solar. Properly sized, shaded, nice thermal mass, and so on. Mike Utzinger might take exception to the fact of proper sizing because that's an awful lot of windows for Wisconsin. And indeed, when the Jacobses originally built it, that was single glazing. And so it was too much window. Now the house has been refurbished. It's double glazing, floor insulated, and it's been brought up to contemporary efficiency specs. And the house works extremely well. Every time the sun shines in the winter in Wisconsin, it gets 24 hours worth of its heat. It's fine. The sun shines 50% of the time in the winter in Madison, Wisconsin, or Middleton, Wisconsin. Therefore, this house reduces its energy demands by 50%. For those of you who wonder why a physicist does so much architecture, I am showing this. Because it was this, living in that house, and the impact of that house that was incredibly important to me. And Mr. Wright was still alive. And then I spent some time at Taliesin and got awfully serious about being an architect, ended up being a physicist, but the love of architecture stayed in, and now you understand why this hybrid stands before you. Well, if Mr. Wright knew how to do the things in 1943 and he didn't take any courses, I'm sorry, Jeff and John and Mike and other people that didn't take any courses, he just did what he called organic architecture, just followed natural principles which have been around for a long time. So we can do those. The question is whether you can apply them to low-cost tract homes. Here is a solar tract home development in Reno, Nevada. This home saves and has been monitored and measured to save 50% of its winter energy use. And these particular models save 30%. So he has the 50% models and the 30% models. And that's the lowest cost house he's got. So this is the starter house. And the energy bills are lower as well. And so he's increased his sales by about 30% by having the solar houses in there so that people can qualify to buy houses who couldn't buy houses otherwise. And you find that solar can affect in a positive way the economics for builders. We know how to do this stuff. All right? Well, if you're using solar, then it says, well, let's just start looking at the advantage of the solar energy that falls on our building surfaces. I mean, if using solar energy displaces energy and reduces emissions in the atmosphere, for goodness sake, let's look at our building surfaces and see what we can do. Well, you've got a need for ventilation preheat on buildings, an industrial building here in Canada. And so you just use an aspirated wall here that preheats with the solar heating falling on it, the ventilation area. This is also in Canada, in Toronto, Canada, and this is an elderly community. And they are preheating the ventilation air to all of the apartments, just using the skin of the building that would have been there anyway, but making it a solar thermal preheater. This is Federal Express building in Littleton, Colorado. They don't necessarily have to be black. It says, look at your buildings and use the solar energy falling on it. Now, I want to back up just for a second because I really practice and believe in what we call bioclimatic architecture. And the proper statement of what I'm saying and what all of you would say is stand on your site and look at all of the environmental resources you've got. Look at the light, look at the solar thermal potential, look at the ground coupling potential, look at the air, look at the natural ventilation potential, look for natural shading, look for all of those things. I realize I'm taking a somewhat narrow view right now and just talking about solar supply, but obviously I'll come back in a few moments. We have to keep that integrated. All right, farmers here in Wisconsin, if you'd like to keep your animals warm, isn't it nice? Just go ahead and use a surface you already had, but turn it into a passive solar collector. Just start using the resource that's already falling on the place where you live or you work. Now, most of us work in commercial buildings, and an enormous amount of the energy cost goes into lighting a commercial building, directly or indirectly, as you know, from the light and from the heat that results from the light. We've forgotten what windows are for. Windows are very nice. They give us a nice view, fine. Tell that to the electrical engineer. Tell that to the person who uses the office. Surprise everybody, windows give light also. Okay? There could be a relationship between these two things. Well, where's the cost of light? It's electricity. If you want to save money, save electricity. If you want to reduce environmental impact, save electricity. Buy the best lamps you can. Don't haggle over their first cost. Buy the longest lived lamps you can. Don't haggle over their first cost. Save that electricity. And of course, this is the best way from a design standpoint to save electricity. And my favorite area and architectural area and my own special area of, I suppose, expertise is in daylighting buildings. I designed our office building in Harvard Square, our national headquarters, and it's daylit. It has 0.44 watts per square foot of lighting power density installed, but it only uses 0.25. We instrument it. So we've measured it. 12 months of the year, the average lighting power density is 0.25 watts per square foot. Because for the most part, you just don't need lights. People will walk into the building and surprise, you've been there a couple hours and you haven't seen any electric lights on. It's possible to do this. We know how to do this. And the energy reductions are huge. They're marvelous. Then you go up to the roof of our office building and you find this thing. This thing. Well, that's a 2.1 kilowatt photovoltaic array. For an office building, that's tiny. At 0.25 watts per square foot, this little array gives enough electricity for the residual lighting for just about 10,000 square feet of office space. This is pretty expensive to put up. But because of our efficiency, we are able to get a big impact for a small, low-cost system. Here is an example of our own experience of efficiency bringing us down to where it was economic for us to finish the job and use some of that energy that would otherwise have been wasted on the roof. And so we move into this area, and I'll move quickly in the interest of time, Casey. But Stephen Strong Saturday is going to be talking about this in detail. But this has certainly become the most interesting new area in solar energy, partly because people relate to electricity, but partly because when you put these out in the sun, They become little batteries. Electricity just flows out of them. And 100 years from now, the same amount would flow out. There's nothing to wear out. If you do your metallurgy and your chemistry correctly, there's nothing to wear out. They just sit there. Photovoltaics. Well, what you can do then is say, all right, let's replace our power plants and have big fields of these things. Well, that's one way to do it. Another way is to bring the electricity close to home and to begin to look at the opportunities for area that we have close to home. Sacramento Airport, for example, isn't that nice? You've got parking lots at airports. Might as well shade the cars while you're at it in a hot climate, so it makes it much more comfortable and produce a great deal of electricity. Minneapolis, Minnesota, okay? Well, you got parking lots, might as well use the top. It gets pretty hot up there, you might as well shade the cars in the summer. And we begin to find that we have the opportunity for the area for these things all over the place. In fact, we come back in close. The closer we can couple our electricity use to where we are and work, the more economic the whole system becomes. So we begin to look at our buildings and say, all right, let's put it on our buildings. And this is remarkable, partly for the fact that it's 300 kilowatts that was specifically designed into the building, and partly because it was done in 1985, which already seems like a long time ago. We're just now trying to promote architecture that integrates solar electric supply into the building. So the weather is hot. By the way, this is in the scenic hot climate of Washington, D.C. All right? So the weather is hot and all the air conditioners go on, and this building takes care of 300 kilowatts of its own air conditioning, which helps unload the utility by 300 kilowatts, so it can help air condition your building, John, because you didn't, no, not John, but other people, because you didn't do this. All right? And so you find that we begin to get a synergy between the economics of creating electricity with solar and creating it on the very places that we use it. And remember that buildings use 2/3 of all the electricity in the United States. It was 66% last year. All right? So you start putting them everywhere. And a few of these are from Steve Strong. They're stealing a little bit of his thunder from Saturday. You've got roofs everywhere. You've got opportunities for PV arrays everywhere. There's Burger King. All right? And the best place to use it, at the beginning at least, is on schools. This is in Pasadena, Monterey Hills School. And there is a major Solar for Schools program, and it's the best place because it affects the kids, it affects the teachers, it affects the parents. It also returns value where public money is being used. It's really an extraordinary starting point. Wisconsin has a major Solar for Schools program, and there are others throughout the country springing up. But then you can go the next step. And you can get the really neat idea of the utility coming out and knocking on your door in a low-cost neighborhood and saying, we'd like to borrow some of your roof, please. May we put something up there? Because here we have a whole neighborhood. This is Gardner, Massachusetts. And we would like to find out what it's like. The power lines are getting overloaded. The transformers are getting overloaded. We need to have some more power out there. We don't want to rebuild the power lines and the transformers. So we'd like to find out what it's like to put the PV out there. This was also done in 1985. And this is engineered and designed by Stephen Strong. This is an advertisement for Steve's Saturday workshop. I will be in Mexico City then and can't see it, but I've seen it many times. And if you can stay, it's worthwhile. Right? So you find that when you start doing the utility economics, the benefits to the utilities, you find that the utilities really ought to be pouring a good bit of money into this stuff to help us defray the first cost. The difficulty is that we're now undergoing national electric utility restructuring or deregulation. It's becoming a competitive field. It's changing the whole view right now. It still looks like the economics of what we will call the distribution utility will begin to look pretty good with helping you with photovoltaics on buildings. The Sacramento Municipal Utility District is really showing us the way, where they've already done 450 houses, and they're doing 1,500 more houses. And they are not just wasting the money of the citizens of Sacramento. All right? This is another one of Steve's designs, the earliest design, the Carlisle House. The interesting thing about this, it's got the complete synergy of what we ought to be talking about. If you want to heat your house, design it for passive solar thermal gain. You want to have sufficient lighting in the house, allow for deep penetration and high penetration of daylighting to balance windows. You want to have natural ventilation, allow for the ability to open windows so you have natural ventilation. And if you want electricity, why not use the roof? there's 7 kilowatts of electricity. This is an energy-producing house. It produces more energy each year than it uses. It was the first one. It was an MIT project, by the way. Affiliated with MIT back then. And it was the first house built that demonstrates we can have homes and buildings that instead of being drags on the grid, they can be contributors to the grid. And this indeed is what I'll call the Amory Lovins model, if you hear the way Amory is talking these days, about how power lines will become power plants will become completely obsolete. Because in our cars, our hypercars, efficient cars plugged into the house is completely integrated, designed like that. Those become the power plants of the future. It's not a model that's totally out of question. This is the Impact 2000 house, also designed by Steve Strong. I thought Steve would be here today, so I put some of his in here. But this is commissioned by Boston Edison to show the kinds of things you could do in the sunny climate of Boston. And what has he done again? He's designed with a 2-story sun space. He's designed with direct gain. He's designed with light shelves to enhance the daylight going inside. He's buffered the west side very, very carefully, the east and west sides, from excessive gain in the summer with proper shading and shading overhangs and shading overhangs. He's put in glass above, but it's solar controlled glass for daylighting. He's put in solar water heating here, and then solar electric there. And there is a synergistic design of all of the various solar elements, a truly bioclimatic design, a building which has so little draw on the utility that its contribution to greenhouse gas emissions is almost gone. Well, to make it easier for us, the solar field is developing building materials that look just like our old ones. For example, solar shingles on the passive solar south face building in Atlanta, Georgia. Shingles that produce electricity. Okay, they look like that. There's a picture of President Clinton holding one of these up. He was really quite astonished, saying, this thing is so thin. He kind of unrolled it and held it up. The more we can have our building components become our electricity providers, the better, because instead of the shingles, you can use that. Or like the shingles the same substrate can be used to make a continuous roll that can go over the top of metal roofs. So there you have a solar electric metal roof. Atlantis Energy has now moved a plant into Virginia and is assembling solar tiles. So you can have a roof of tiles. This is 1 kilowatt. If you want to see how big 1 kilowatt is, that's a 1 kilowatt array. This is an energy efficient house. It only needs about 2 kilowatts. So there's 50% of the electricity provision in Sacramento from the roof. And isn't that nice that you could tile the roof instead of doing that? Now this is Sacramento, so it uses light colored shingles there. Well, it's not light colored here, but it is lifted up so the air can flow underneath and cool the PV, and it shades the roof. And so it does double duty. It's very nice. This is a little tract home I designed. I couldn't find pictures of it. I should have put it in Nevada. But the house is turned all wrong. It was a wonderful design problem because the house is lined up north-south axis. I couldn't get past with solar. We slid the garage around, said at least do a little solar electric. And this amount of sun tiles with a very energy efficient little tract home in Reno is giving 50% of the electricity for the house for the year. Okay, a $5,000 system, not much. Now we begin to see synergy opportunities then between providing solar energy and solar electricity in our bigger buildings. If you have daylighting, you need shading. Here we are on the south side. We need shading for our buildings. As long as you're going to pay for the shading device, why not have it go backwards. Why not have it produce electricity? So that's an 18 kilowatt array, and this is in the sunny climate just out of London, England. Okay? This is the new British Petroleum plant. And I know BP has been helping support this whole wonderful show outside that I for one, I brought my camera right down here. I'm looking forward to seeing. And these shading devices here are all solar PV arrays, are all PV modules. And this is solar glass. The glass, the curtain wall glass, is producing electricity. Greg Kiss was the architect of that, and Greg Kiss will be the other speaker on Saturday. So if you want to realize that both Steve and Greg, as they give the workshop, have enormous experience in designing these things. This is the entryway to the Olympic Swim Center in Atlanta, Georgia. and you like to shade people going in, and that's fine. As long as you're shading them, you might as well use fritted glass so that you get a kind of nice, soft daylighting. And if you're going to frit the glass, why not frit it with little solar cells? If you go through Chicago and the United Airline terminal, and I keep looking at all those little square patterns and thinking, oh boy, wouldn't that be wonderful? Think of all the electricity we could have produced. You're already going to pay to put the glass in there. So what you're paying for the electricity is just the differential cost between putting the fritted glass and the photovoltaic fritted glass in there. And so we're beginning to find combinations now. This is in Germany. They're putting PV on the roof, and this is glass photovoltaic curtain wall in between the windows. Yes, there's not enough shading in the windows. The Germans love mechanical things. I'd like them to sort of combine a few other things like shading and so on. Oh, this is solar control glass. But you're beginning to find that we have these components we can use now and integrate with our other solar technologies, which are pretty great. So there's your curtain wall, your PV curtain wall material. Right? This is the Sanyo headquarters in Tokyo. This is regular glass. This is photovoltaic curtain wall glass at the top. And the first example we have is right here on Times Square. And this is 4 Times Square building that's going up. And this top part up here has got photovoltaic curtain wall glass. It'll be the first application here. And the architect who worked on this project, who's responsible for the PV, again, is Greg Kiss, who will join Steve Strong Saturday. So if you can stick around, I know I'm making a big advertisement, but these are people who can be real resources to answer your questions about what's the state of the art of the technology out there, and how can I use it. Well, let's now finish this off by looking just at sustainability and how we can come back to that concept of sustainability. That's enough technology now for a while. This is something that's been around a long time. Cliff Humphreys did it 30 years ago. Some of you as old as I am remember Cliff. And I still like to use it. It's very similar to an approach used by a wonderful organization called Natural Step, right now out of Sweden, that's in the US. Cliff said, look, we have a life support system capability, and we have a drawdown on that. And as we put more and more demands on the life support system, the problem is it doesn't just sit there being capable. It gets drawn down. We have more and more demands to grow more food on the soil, and we diminish the productivity of the soils. And we have erosion because we till the soils, and we cut down trees and so on. So the greater our demands, the more we draw down. Somewhere, we either have hit or are going to hit there. 30 years ago, Cliff guessed we were there, but it doesn't matter. Somewhere, we're going to be there. Now, here we are. We are trying to turn the corner into redefining everything that we do to be sustainable. The Earth has got a marvelous resiliency, and natural systems have a marvelous resiliency. And the hope is that if we reduce our impact on the Earth's systems, that we can have a rebound of soil fertility, a rebound of our forests, a rebound of our ability to grow food, all right, and a cleaning up of the Earth's water, and a cleaning up of the atmosphere. All of that is this line. And the hope is that we can level our impact at a time when the Earth can recover sufficient that it can support us. The survival gap says that this is a sustainable situation. What bothers me is we don't know where we are on this. We don't know if we're here, we don't know if we're before there or after there, but it doesn't matter. We're in the stupid situation where we have to just hope that we're doing everything in time, and we have to hope that we can recover to support up to 10 billion people of the Earth with good standards of living, good food, good health, good equity, good opportunities. A little scary. So we look at a definition, a variation of the definition of sustainability, and here it is in the energy sector. To say that a development is sustainable means at least that its patterns of production and consumption can be reproduced indefinitely without doing irreparable harm to essential natural ecosystems. That means we can keep doing what we're doing as long as it doesn't do irreparable damage to the essential systems. I guess lizards, frogs, I mean, they're probably not essential. I guess a little dirty atmosphere, a few people dying of air pollution, that's not irreparable, you know, all right? This is kind of the way the definitions of sustainability are being tossed around. This doesn't move you. If you're trying to get people to take sustainability seriously, we've got to quit using these doggone definitions. This basically says you can continue to do business as usual, just do it less. You can't continue to do business as usual. We've got to change the very basis on which we do our economy. Okay? We sell the earth in order to power our economy, and if that isn't long enough, we'll sell the future while we're at it too. All right? We have got to change the basis on which we're building our economy and operating our economy. Now, I want to go back to the electric car. So there's a reason more than just showing off. The picture of my little EV1 at the beginning. And that is that if we say, all right, let's do responsible things. Let's all go out and start driving electric cars. Fine, here's the amount of coal you start with. Here's the amount of energy you lose in the coal to process it. And then you make electricity, and then you send out the electricity, and then you put it through the motors and the batteries and transmission. And you find an electric car is 16% efficient in terms of primary energy if that primary energy is coal. And all of a sudden, you're driving yourself around in an electric car, and all you're doing is exacerbating the emissions, the climate emissions. You're helping locally, but not globally. Well, what you've got to do, let me just give you a number, by the way. In California, we have a very clean supply, spectrum of electricity supply. And if I do calculate the emissions from my electric car, it's equivalent to an 80-mile-a-gallon car. So if you have basically a clean electric system, then it works pretty well. So having my EV1 in California is like having an 80-mile-a-gallon car in terms of the emissions going in the atmosphere. So it was a good thing to do there. In other states where you've got more coal use, it becomes less and less. So it says we got to get away from this. We have to start doing things that don't require that, because this is where the economy goes. That is a real crossing. I couldn't believe it. When you come in from the Aspen airport and you look to the left, Power Plant Road is one of the main roads. I couldn't believe it, and I was so excited about that I didn't see that solar home in the back. Okay. Now, Sacramento Municipal said, we realize that you've got to bite the bullet. And they turned off this expensive dog, 800 megawatts. They had 5 electricity rate increases the first 4 years to compensate for the fact they had to buy power, but they bought power while they began doing their transition. And it is now less expensive than it was before they turned off the power plant, and Sacramento Municipal is the nation's leading solar utility. You have to take that first step, and it has to be different from the power plant. So sustainability of renewable energy, this is the number down here. The question is to ask, do we have enough? Well, if the sun each day gives 15,000 times as much as all the society needs, yeah, we probably have got enough. Okay? Then, how do you clean up the act with the electric cars? Just go back to the source and see to it that the provision of the energy doesn't itself cause problems. In other words, just as we think in systematically, or as systems with buildings, from passive solar to solar water heating to gain to natural cooling and so on, we have to think of systems here. And if we're going to do the electric cars, we also need to take responsibility for providing that electricity, as Sacramento Municipal does, in a clean way. We have to take responsibility for the whole system. If you like breeder reactors, fine, you can have one. Here's one in Frederick, Maryland. It's got 50,000 watts. It's SolarX plant. 50,000 watts of PV here. And they use the electricity from that PV in order to make more PV cells. So it breeds itself. So there is a breeder reactor where they're responsible for the whole cycle. Right? The costs are coming down dramatically. And they're going to come down more as we build the market. But the problem is it's a moving target. And as we bring the cost down, utilities and energy companies keep lowering their costs. And then they say a few cents per kilowatt hour. That's a big difference, folks. Well, let's put that in perspective, too. Suppose you want to use your camera. We're going to go outside later, and I'm going to take pictures. I am willingly paying $7,000 a kilowatt hour for the right to use my camera. Whenever you use anything like a CD player with AA cells, you are willingly paying $1,600 per kilowatt hour for that electricity. Flashlights, $250 per kilowatt hour, and so on. All right? In other words, you don't care about the kilowatt hour cost because it's the value that you relate. In order to make the shift, we have to equate our energy use in economics to value gain. We're down here in the noise level. We're talking about 14 cents and 15 cents and 18 cents versus 10 cents or 8 cents or 4 cents. All right? And the value difference of what we get for society from renewable energy is way, way up here. We're using the wrong language. Sustainability is not a matter of just telling people we've got to sort of equate demands with resource availability. It's a new language of value in life and value in living in harmony with an earth that supports us and that we begin to support and learn how to support back. So when we do our solar in our schools, for example, we're telling the kids that it's important to us, your parents, to show you what's going to be available for you. We're doing this for you, kids, because you're going to be our leaders and you're going to help us power this transition. And the kids at the solar school in Pasadena, they renamed their school the Solar School. And they have a song, a theme song, like a football song, rah, 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 but it's celebrating the PV panels on the roof. It's the Solar School song, right? And you begin to get a sort of new sense, a new relationship, going back to the way Casey introduced this whole thing, between the kids and future generations and the earth and the sun that's sort of wrapped up in a systems perspective, not of technical things, but of ethics, The sun does more than just give us life support. It gives us love support. The sun stays with us at all levels of our lives. It supports everything we value as well as the things that we need. We have lessons we can learn from nature. And if we need to build solar electric devices, we can look at flowers very carefully. Gee, isn't this interesting? It's a 2-axis tracking solar collector. And so Stephen Strong just put up a system in Northern California that said as long as we're going to build our energy systems, even if they got to be ground mounted, why not make them pieces of moving sculpture? Why not at least emulate the beauty of nature? And Steve got a lot of flack from people who said, come on, these things are white and these are black. What are you doing? And these are black. And they got a lot of static from people who said, they call it Steve's Folly. And it's up, and this is going to be one of the most famous systems in the world. Because when you approach it, you see this beautiful field of man-made sunflowers emulating the capturing of nature. Here's Steve and his associate Rob Erb. Okay? Now, the final view is who is nurturing whom. The earth is nurturing us, but the earth needs us more now to turn our nurturing attention back on it. And in essence, the earth is now asking us to help give it a rebirth to itself. Well, we give birth to these people who then know how to nurture and love the earth. And through that, we get this connection that we need. Thank you very much.
Global Possibilities is an environmental nonprofit dedicated to promoting the use of solar energy in the United States to reduce our dependency on fossil fuels and mitigate climate change through consumer education and sustainable design curriculum development. As a national solar energy advocate, Global Possibilities organizes and facilitates national conferences, educational initiatives, and public outreach in collaboration with academic institutions, nonprofits, energy experts, business leaders, and government. These partnerships are designed to ultimately build public awareness and understanding of the benefits of solar energy and sustainable design as it relates to the humanly built environment and our overall quality of life.